record. Oh, I guess everyone gets a message. Count me. Okay. That's a new feature. Only took them a year to do that. Organic Chem 2 as a second language was yeah, that's yeah, I try to interact with chat. So like I have like a second screen open. So for the most time I keep up with the chat, but if I don't, you know, feel free to just open your mic and ask something. Okay, so before we even get started with a little bit of the chemistry, pretty sure there should be an acid-base reaction in here. Should probably like formation of ethers in acidic media, which is actually the industrial way of doing it. So I'll go and kind of reiterate these kind of principles, I guess, of organic chemistry, which is that what would be the best way of explaining it without going too in depth? Okay, so in acidic, oh, by the way, my handwriting I know is chicken scratch. So if there's something you can read, just say for me to rewrite it or ask a question about it, right? So in acidic media, right? You will form. And there are very few exceptions to this, but for the most part, it holds true. You'll form positive species. We'll probably get to examples of this today. And then in basic media, you will form negative species, right? And if you think about it, it kind of makes sense. Well, it doesn't really kind of make sense. It does make sense. And that's because acidic media, by the way, media, I guess is another term for like environment or whatever, right? So when you're in conditions, I should say conditions because we're doing chemistry, right? So when you're in acidic conditions, right, you have acids, right? And what are acids, right? In simplest terms, I guess the Bronsted, yeah, proton donors, right? So you have an abundance of H plus in solution or in your reaction flask or whatever it might be, right? So any reaction that occurs, right, it's going to be happening in this very positively charged environment or the lack of negative charge essentially, right? So if you have things that are negative, right, or have a lot of electron density, I don't really like saying negative. I always feel like describing things through electron density is a lot better way of approaching it, right? So things that are rich in electron density, right, they're going to attack the protons, right? Which means things will always have positive charges, right? So that's what I mean by positive species, right? So example of this is like, I don't know, if you put like an alcohol, right, like sulfuric acid, right, that's going to get protonated to ROH plus, right? And really anything that has lone pairs that could accept a proton, right, will get protonated. And you're going to see this in mechanisms a lot, especially when I think it's chapter 16 or no, not 16. I think it's like 19, 20. I mean, you're going to see it in all the chapters, but it's very, very useful in the later chapters where there's like 6, 7-step mechanisms, right? And a good way to always remember your mechanism is like if you're in acidic media, right, everything will either be neutral or positive, right? If you form a negative charge thing, you probably messed up somewhere, right? Because if you form something that has a negative charge in it, right, it's instantly going to get protonated, right? So that's why I always try to go over this. Actually, someone in our lab group told me about this, and I always kind of kept it in the back of my mind. He called it like the golden rule of mechanisms, right? And the same thing occurs in basic media, right? When you have like things that are very rich in electron density, like hydroxides, I don't know, well, the one you guys just learned, hydrides, or, very strong bases, right? They're going to have negative charge. Did someone say something?
Yeah. When you meant like in an acidic media or medium, you mean like is it like the thing that the base or like bulky base, something like that with the thing above the arrows.
Yeah, exactly. The
Am I
reagent,
making any sense?
right? Yeah, no, I know what you mean. But yeah, the thing above
Like,
that,
you know, in a mechanism.
yeah, so like if you're given a reaction scheme, right? So one thing, I guess, a quick review from Orgo 1, right? There's reaction schemes and there's reaction mechanism, right? A reaction scheme kind of looks something like this. If you had, let's use proper stuff. So let's say we had ethanol, right? And we put it in, I don't know, some sort of acetic acid or whatever, right? So this stuff, right, the stuff above the arrows, as you say, right, these are other reagents, right? Generally, you put this is your substrate, right, the kind of molecule you're doing your chemistry on, right, and the reagents are interacting with them, whether they're catalyst, whether they're, you know, an electrophile or nucleophile, right? They're everything else that's present in the reaction, right? So by acidic media, I mean any reaction that has acids present in it, right? You'll always have positive species because you have it at abundance of H plus. Does that make a little bit more sense, hopefully?
Yeah, it does. And just to clarify, because I always like get mixed up with like reagent and substrate, like all the vocabulary gets kind of confusing. So the H2SO4, that's called the reagent. Like whatever's above the arrow, that's called the reagent.
Yeah, I mean, technically anything in a reaction is a reagent, right? But generally the way schemes are written is like your main substrate, right, is the one that's before the arrow, then everything else is like other reagents, whether that's a catalyst, whether that's the electrophile or nucleophile or any like a solvent, right? So if I had this in like H2O, right, H2O would be the solvent, right? So generally it's written like that. Sometimes they could write it all above the arrow, right? But yeah, those are all like reagents that are part of the reaction. So in this case,
Okay, thank you.
sulfuric acid will be your proton donor or acid. Water is just your solvent that's going to be in it. So I guess we could just write reagents there, right? So this is a quick review of that. So this is a reaction scheme, right? So let's say this gives us OH2 plus, and then, you know, you could do whatever. If I put in some other nucleophile or something in there, you know, you could have a reaction with this because OH2 plus, as you guys hopefully remember, is a good leaving group, right? So that's a scheme, right? And then a mechanism is when you show actual electron movement, right? So I guess this is a quick Orgo 1 kind of review. So now if I this grab your proton, this returns here, right? And then boom, you have now protonated OH2 plus or whatever, right? And then you keep drawing arrows for whatever else reacts with it, right? That is now a mechanism because you're showing electron movement, right? So yeah, schemes are a lot simpler generally on your exams. When you do like a multi-step synthesis problem, right? He's just asking for reaction schemes, not the mechanism. Usually it'll always be indicated when you need to show a mechanism, right? So just a quick looking forward to for your exams, there's usually, I mean, it kind of depends, but there's at least always one mechanism question where you have to show arrow movement like this. And then there's always one multi-step synthesis where you have to kind of recall the reactions you learned about, starting from original product, ending at some other, you know, starting from original starting material to some product that you get, whether it's 3, 4, 5 steps, however many it might be, right? So kind of reiterating Orgo 1 stuff, right? Schemes and mechanisms, they're different things. Schemes is just the general outline. Mechanism is the detailed electron movement, right? So anyways, back to what I was saying, the basic media, right? If you have things that are rich in like, you know, hydroxides, hydrides, strong bases, or very strong nucleophiles too, I guess, right? Things are always going to be negatively charged, right? Because as soon as you form something with a positive charge or whatever, whether it's a base or a strong nucleophile, it's going to be reacting at that position, right? And like I said, this is just something I wanted to talk about now because you're going to constantly see this over and over, but especially I know in your later chapters, like when we learn about aldehydes and ketones and enolates, you're going to see this come up a lot where you're going to draw mechanisms, right? Well, that's actually, I'm glad you brought that up there, Eric, about memorizing, right? So those who have had me before know I do not like when people memorize. And I get it. Everyone has different ways of studying stuff, right? But if you kind of always remember the logic of a reaction, or really not even just a reaction, of just, you know, the chemistry really, whether it's a nucleophile interacting with electrophile, an acid or a base, there's something that's a catalyst, right? You don't have to memorize a mechanism. There can only be one logical way things can go. I mean, for the most part, yeah, there's only one logical way things. So I wouldn't say to memorize particular mechanisms, as far as I know. Maybe when we get to like Diels-Alder and stuff, there's certain arrow movements you have to memorize, right? But yeah, we'll get to that soon, especially later throughout the semester. But this chapter is relatively easy. Actually, I'm kind of glad they always start with this chapter, because it's like, it's not too difficult of a chapter that like on the first day of class or second day, whatever, when you start learning about this, you're just like, oh man, I don't remember this and that, right? It's still kind of like SN2 type reactions or whatever. Someone asked, first step is to deprotonate when there's an alcohol. It all depends on the reaction, and what kind of product you're going for. But generally, usually protonation occurs within the first two steps. It all, like I said, it all depends on whatever original substrate it is and what you're trying to do with it, right? So, okay, let's get into the chemistry at hand here now, which is we're going to start with some ethers, right? Let's make that a little neater. So ethers been around for a long time. I think for the most part, most of the kind of research that was published on it was done more predominantly in like the 20th century, or no, it would be 19th century, right? It's 1800s, right? And that's kind of when science in general started to become recorded a lot better. But yeah, you know, they've been around. Like ethers you kind of see them everywhere, right? Like you could see them in, I don't know, it's cosmetics, perfumes, biological molecules, drugs, right? It's a very commonly found group, right? In terms of nomenclature, so this class, and generally for recitation, I don't really cover nomenclature, and you're not going to be tested on it. I'm pretty sure Professor Biscoe probably told you that already. But it's one thing I like about his teaching style, right? Is that, now don't get this confused with not being responsible for it, right? Because if he asks you on a test, like if he names a compound, right, you might have to convert it to its, you know, bond line structure or whatever, right? So understand the nomenclature, right? But you're not going to be directly tested on it. That's kind of the key thing I want to go over with you guys. So can really skip that part. Let's get into direct reactions, I guess. I guess we can start with the most basic one, which is acid catalyzed reactions, right? So let's find some problems here. For the most part, his exam problems are kind of similar to Klein's. If you don't already, or I should say, if you haven't already looked at it, like all his old exams, the one in the organic 2 folder, they're basically all of Biscoe's old exams. And then there's some that were made by Andia, but they were in the same style that Professor Biscoe teaches in. So literally everything in the organic 2 folder under the old exams is stuff that you could practice that should directly help you with the exams you're going to get in class. Okay, so let's start with, I guess, I got to find some problems here. Well, they don't have any for the acid catalyzed version, but that's fine. I could just make one up. Okay, so let's see. We have this. I guess this would be 1, 2, 3, 4. I guess technically secbutyl, secbutanol. I don't know what the proper name would be, but this is a secbutyl group, and that's a OH, so it'd be secbutanol. Right, and let's say we wanted to turn this into an ether, right? So in this case, right, you're going to see this written many ways. So I'm going to show you kind of all the ways. The most common way, and I think usually Professor Biscoe kind of leaves it like that, is if you see H+, right? You could also see H3O. Oh, maybe let me write this all differently so people don't get confused later on if you're viewing this later. So you could see it as H plus, which just means any acid source. Sometimes it's written as H3O plus, and maybe sometimes it'll specifically mention the acid. So I will write H3PO4 because in industrial applications, this is what's used. It's a solid acid catalyst, usually done in like a large scale reactors to produce ethers at like a industrial level scale. So all these represent the same thing. It's essentially just a proton source, right? No, so this is not Williamson ether synthesis. This is, I guess, technically acid catalyzed ether synthesis or whatever you want to call it. Essentially what you're going to do is you have any sort of alcohol, right? So I will kind of generalize this as an ROH. If you introduce it to, this should work for this ether for the most part. But if you introduce it to any sort of acid catalyst, then what you will do is you have ROR formed, right? And the kind of limitations of this reaction is that you could only combine the same R group with each other, right? So in this case, right, you're going to see on the other side of this molecule, we're going to have that same R group, right? So it's useful for making stuff like ether, which is just diethyl ether. It's commonly called ether. It's a very, very commonly used solvent. Like I go through it every week. Well, not like the full bottle, but like our lab uses it a lot. Most labs use it a lot. It's great for column chromatography. It's great for doing reactions great for doing workup, right? It's a very commonly used ether, right? So that's how these are kind of made. This is like the industrial version of making it. And this should, I think he probably, I mean, he should mention it, but well, it's so useful because this is an easy way and cheap way of making ethers, right? Because the Williamson ether synthesis, which we're going to get into next, new examples of, right? It uses a base in an alkyl halide, right? Which requires kind of, depending on your base, it requires certain conditions, right? This on the other hand, just uses an acid catalyst, and usually, it depends on kind of the reactor you're doing it in or whatever. Usually it's like a catalyst bed, and then you just put your alcohol in it, and then you run that at a certain temperature, right? And it's literally just going to react with itself, and then you could distill out the ether, right? And you get basically a mass scale production of an ether. Your book probably has an example showing this, but for like diethyl ether, right? But you could probably make very common ethers out of it. I just want to use a different example just to show you that it works for kind of any ROH. I mean, I'm sure the yield will probably go down with something as big of a group as this, but for the most part, it will probably work. But yeah, the main advantage is that you can make ethers kind of cheaply using this way. But the limitations is you can't choose the R groups. That's where the Williamson ether synthesis comes into play, because then you could have distinct R groups, right? So anyways, what happens here is, let's draw some electrons. I will use H plus for simplicity's sake. So like I said, you could do any of these. If you choose any of the bigger, like not bigger acids, the other representations of acid, just make sure you draw a second arrow to return the electrons, right? But if you're using H plus, it's very simple because you could just draw one arrow like this. This gets protonated, right? Get something like OH right here. So now we have, I guess technically this is an oxonium ion, right? Now you have, in this case, something that is a very good electrophile, right? Why is this a good electrophile? Well, think about it. Oxygen, is oxygen like being negative or positive? Let me ask you guys. Negative, right? Or the dash side. So yeah, oxygen likes its electrons, right? It's very electronegative. You know, closer you get to fluorine, the more electronegative is. Those more atoms are kind of stingy with their electrons, right? So now you have a positive charge on oxygen, right? Which means that it does not like that, which means it's going to draw electron density from somewhere else, right? Which makes this carbon partially electropositive, right? Because electron is essentially withdrawing its electron density from it to stabilize itself better, right? And now this carbon is partially positive, right? Which means at that position, this molecule is now electrophilic, right? So we turned a neutral molecule into an electrophilic molecule, right? All by protonating it, right? And this is why kind of acids are useful, right? Because if you protonate certain groups, carbons or, yeah, for the most part, carbons next to it become more electrophilic, and then you could do a reaction at that position, right? So now what happens is now you formed an electrophile, right? And remember, alcohols, right? They're kind of like moderate nucleophiles, right? They don't have a full-on negative charge, but they have electron density at that OH position, which means they can attack things that are partially or fully positively charged, right? So in this case, another molecule of the original alcohol is going to come in. So we're going to draw this here, and we'll draw it the other way to make it a little bit simpler. 1, 2, 3. Yep, okay. Draw electrons, right? And now it's going to attack this electrophilic carbon, right?
Wait, where did that other molecule come from on top of the arrow?
Okay, so this is originally here, this is our kind of like reaction mixture, right? Remember, in a reaction mixture, we have like moles of all these molecules, right? Which is what, 6 to the 10 to the 23rd or whatever, right? You have literally trillions of molecules in there, right? Now, not every molecule is going to be instantly protonated, right? It's only going to be ones coming directly into contact with the acid, right? So this is one thing I understand about chemistry. It's happening at a very fast like scale, like kind of like the femto or picosecond scale, right? So all this is happening relatively fast, but when you go down to the molecules, it's kind of happening one by one, in a sense that the original alcohol is going to get protonated, and another molecule that's just sitting around there that hasn't been protonated yet will be attracted to this now, right? And this kind of all happens in a reaction vessel, right? So one thing I always try to iterate about chemical reaction, it's not this, when you write it on a piece of paper, yes, you're drawing one substrate or whatever, but you have to understand that that molecule, there's a lot of those molecules present, right? So just because some chemistry happens on it, right, doesn't mean another molecule will be protonated or reacted the same way. It might react with itself, which is what happens in this reaction, right? Is essentially what you have is all you did was introduce acid to the like mixture of this alcohol, right? Some of it's getting protonated, and at the same time, the other alcohol molecules that aren't protonated are attacking those protonated ones, right? And those form the ether, right? And if you do this correctly, right, if you basically set this up with a still, right, you could evaporate the ether quickly, right? And that exploits Le Chatelier's principle, right? Because the final product is an ether, right? And if you're evaporating it out of the reaction vessel, right, the reaction will push forward or push towards the left, the right, right? So just one key thing to remember about reactions in general is just because you draw one molecule on a paper, does that mean that's the only molecule present? And this is going to be very important in enolate chemistry when we get it to it later in the semester, because those are also reactions involving molecules that react with themselves, right? So just kind of have that in your back of your head, is like, just because you wrote it once on your paper or whatever, doesn't mean that's the only molecule present. There are literally, 10 to the 23rd amount of those molecules, right? And not all of them are instantly being protonated, right? Some are being protonated, and at the same time, some are reacting with those protonated ones, or whatever your reaction might be, right? So just going forward, always remember that. For the most part, generally your substrate, like you'll do all your chemistry on it, right? But sometimes it could react with itself, right? That's actually a process called dimerization or whatever, when a molecule reacts with itself and forms the dimer, right? So in this case, right, we have a protonated alcohol here, and we still have the regular non-protonated alcohol still floating around in there, right? So they find each other, go through an active collision and react, right? So now hopefully everyone remembers the arrow movements, right? But alcohol here, right, rich in electron density, we have a partially positive carbon. It's going to react at that position, right? And then at the same time, remember, carbon can only have like 4 bonds, right? So if you're bonding here, something has to be kicked off, which is the leaving group. In that case, water is going to be kicked off, right? So now the alcohol is essentially reacting with itself, right? And now you form an ether that will look like this. O. There should be an H here. Yeah, so in an acid catalyzed reaction, right, the only things present are whatever ROH you have, whatever alcohol you have, and the acid, right? So it's going to be the same R group on the molecule, right? So that's why industrially this is a very useful reaction, because for symmetrical ethers, right, ethers that have the same R groups on both sides, right, why should you use the Williamson ether synthesis when you could literally just put in, put some acid in there and boom, it'll just react with itself, right? But like I said, that's also its limitations, because sometimes you want unsymmetrical ethers, right? So this would be stepwise, right? Because, well, good thing you brought that up. So once again, to reiterate, so some parts of this mechanism are stepwise, some parts are considered. Total, this is a multi-step mechanism, right? But the first step is just one step. The second step here, right? What type of reaction is this? If you look at the arrows, what's happening? SN2. And what's the type of mechanism for SN2? Concerted, right? So in this second step, it is concerted. In the first step, it's just one step. It's just protonation, right? So overall, I guess technically the reaction mechanism is stepwise, right? But parts of the mechanism themselves can be concerted in what's happening, right? So this is the thing to remember, right? This is not like simple reactions anymore where, you just have an electrophile and nucleophile and it could either go SN1 or SN2. You're going to have a combination of different stuff, right? So over here in this place where I put the arrow, it is SN2 happening over here, right? This alcohol is going to attack here, right? And this leaving group will kick off at the same time, right? So let me actually mark that there. That's an SN2 reaction. The first step is just a simple protonation. Is it really SN1 or SN2 or anything in that case? So I guess the total reaction, well, actually, I don't want to really classify the reaction order, because then that gets into something like called SN1 like, SN2 like type reactions. So, but probably the rate limiting step in this reaction is probably going to be that first step anyways. So anyways, are we missing something here on this molecule? The pink one or purple one, however it looks like on your screen? Or is that the final product? Positive charge, right? Conservation of charge. I've taught this in Orgo 1. And I'm sure not everyone here has had me, but whenever you're reacting things to each other, remember the charge will always remain the same. Here we had a positive charge here, right? This is the neutral molecule interacting with the positive molecule. The product must still have a positive charge somewhere. And it makes sense here because this oxygen here is neutral, right? It's going to give its electrons to form a bond. So it's going to gain a positive charge, and these electrons are leaving to make this water neutral, right? So your tests are partial credits. Just be careful in your charges and stuff to make sure.
Sorry, can you re-explain that? You said that the one on the left side was a positive charge, and then the oxygen, the alcohol was a neutral charge. Mm-hmm. And when they connected, it's still a positive charge. Yeah,
no worries. So okay, let's kind of go into more detail here. So the oxygen is attacking at this position here, right? I wish I could draw this arrow again, but this arrow here that I marked, right? This OH group currently is neutral, right? Its lone pair is just a lone pair, right? Now it's bonding to a carbon, right? Which means essentially it's giving up its lone pair to form a bond, right? Which means this oxygen can no longer be neutral, right? Because it's losing an electron to form a bond, right? Therefore, it's gaining a positive charge if it's losing an electron to form a bond, right? And that oxygen, right, the one that's part of this arrow is actually this one right here, right? Because that's what formed the bond. And what got kicked off was this OH2 group. And now if you look at this OH2 group, the O is positive here because it was protonated, right? Now it's gaining 2 electrons back, right? So it'll have a lone pair and become a neutral water, right? So if you want, I could also draw this here. Water will also be a kind of byproduct of this step, right?
Yeah, but I thought like the lone pairs, even if they were to turn into like a bond, the oxygen is still having two electrons because of the bond is technically like 2 electrons, right?
Yeah, so like if it's a lone pair, like on a neutral molecule, right? It's neutral because what is it? The valence electron theory or whatever, however you no, formal charge. There we go. That's the proper terminology for it, right? When you're calculating formal charge, right? If you count all the electrons and the shared electrons, oxygen originally has a formal charge of 0, right? And then when it bonds to carbon, technically now one of those electrons is participating in a bond, right? You're right in the sense that both those electrons are still part of the bond, but now one's technically on carbon side of the bond, one is technically on oxygen side of the bond. So when you calculate formal charge again, right, you're gonna see that it gains a formal charge of +1, right?
Okay.
Yeah, hopefully that explains it. But that's something I think should be in chapter 1 or 2 if you want to do a quick review of formal charge. But that's essentially what's happening. You're right that the electrons are still there. They're not vanishing, right? It's just how they're being shared is different, right? So anyways, positive charge there. And then the final step is just deprotonation, right? Now you could show the mechanism for this step or not. You could also just write -H plus, ask your professor what he's cool with. But I'll just show it just to reiterate. Oh, whoops. So let's say water, right, would act as a base in this case, and it will grab an electron. And then you get your final product, which is an ether. Let's get rid of that. And then the ether looks like this. I'm missing 1, 2. There we go. All right. And that's your final product. It's a symmetrical ether. I guess this would be sec-butyl ether or sec-pentyl. I'm not sure. I forget how that name is grouped. I think it should be sec-butyl. But yeah, this process is only good for smaller ethers, probably like I just use this example because I wanted it a little bit different from the book or probably what you already saw in class. But like this would work for like something like diethyl ether. That should be in your textbook. Methyl ether probably would work with methanol as well. Propyl ether, so that's 3 carbons, right? Very small term ethers, right? This group might be a little too big, but the main point is getting across kind of what's happening in this reaction, right? You're protonating an alcohol, right? The alcohol will react with itself and then form an ether, right? And because ethers have very low boiling points, right? Because they don't participate in hydrogen bonding, right? That's why you could set this up with a still, right? And you could easily kind of evaporate and distill the ether, right? And then this reaction will just go forward. Because normally it's kind of an equilibrium process, right? Whenever you're protonating something, like it will reach a certain equilibrium. So how do you get a lot of product? You remove the product, then more product has to form. And speaking of Le Chatelier's principle, right? Well, actually, it'll come up in a few minutes again, which kind of gave away a hint. But anyways, let's go into kind of a more something that's probably almost certainly going to be on your exam, which is Williamson ether synthesis.
That water in the end came from when we kicked off the water originally, right?
Exactly. And there's probably also water just floating around in general, because generally when you have acidic conditions, it's in some sort of protic solvent, right? Whether that's water or methanol or ethanol, right? But in this case, most likely would be, well, no, in this case, it would be either the alcohol or water, right? So technically you could have another molecule of the alcohol also deprotonating it here, right? That's also possible, right? I generally just choose water as the deprotonating base because it will be present, like we saw here. It technically is a byproduct, but it shouldn't really matter. You could have technically used another alcohol molecule to deprotonate it. It wouldn't be an issue. Anything that could function as a base will deprotonate it, right? I've been used to always using water because I know it's always part of the mechanism.
Yeah, that's why I get like really confused and overwhelmed, because I just feel like sometimes like the professor just brings up random stuff and it just comes out of nowhere throughout the mechanism, and I'm just like, where did this come from?
Yeah, no, I feel you on that, but that's what I'm saying. I mean, you're in class to ask questions, right? So even during your lectures, ask a question. I'm sure he'll be fine going over with it. So anyways, let's get to Williamson ether synthesis, which is actually something I did this week. Because no, we'll actually use that as a problem when we get to it. So Williamson ether synthesis is generally when you have this ROH, right? Now your book and probably in your lecture, you probably use sodium hydride, where it's kind of a reason why they use sodium hydride, but practically now, people try to avoid using sodium hydride. Can anyone probably take a guess why people wouldn't want to use sodium hydride? And then we have, so actually, let me label these a little differently. So we have R1 and R2, and this would be X, right? Yeah, so your base and your electrophile, right? So this is Williamson ether synthesis. I think sometimes in the 19th century, this guy was a British dude. It's actually an interesting thing about, what's it? I think it's Alexander Williamson or whatever. You could probably find it online or whatever, but like trained a bunch of students from Japan, right? And then they ended up going back to Japan, and that's how I guess feudal Japan or whatever, they learned a lot of stuff about science and chemistry, right? And he actually got a bunch of students to that. Could probably find it online, maybe on his wiki page or whatever. Just a like little interesting tidbit of knowledge. Anyway, so this reaction basically involves an alcohol and an alkyl halide, right? And basically what Williamson discovered was if you deprotonate an alcohol, right? So here I'm leaving this as NaH, but really you could use any base. So I'll just write strong base. Preferably, and I'll cite this, preferably non-nucleophilic, right? R2X is just distinguishing the R groups, right? Maybe I should use the prime letters instead. So if this was, so if this was R, this would be R prime, right? That's usually the general notation, but I was using 1 or 2, but I could see how that could be a little confusing, right? But it just means this is a distinct group on the alcohol, and this is another distinct group on the alkyl halide. That charges are conserved across individual run steps. Yes, right? So if you're reacting like, something negative and positive, right? They're going to come together and form a neutral charge. If you're reacting something neutral with something positive, the product will be positive. If you're reacting something neutral with something negative, the product will be negative, right? So that charge is always conserved unless you take you use something to remove it, right? But still, technically, that charge is conserved because now it's just moved to whatever that other final thing might have been, right? So Williamson ether synthesis, right? Still used throughout the day, just in different forms, right? So basically what happens is you can turn this alcohol into an alkoxide, right? So that starts in the first step, right? Let's use an example from the textbook for this. Okay, let's do this with cyclohexanol, right? So this is not actually a direct example from the textbook. I'm just kind of modifying it so we could do it. So if we had cyclohexanol here, right? And we wanted to form an ether out of it, right? Or let's just say the reaction steps you were given were NaH, right? Followed by, what would it be? Let's use Cl, why not? Though generally iodides would probably be better because it's a better leaving group. Yeah, I'll probably stick with the books thing, make that iodide. But iodides are like alkyl iodides are kind of a little bit more expensive, but they're better electrophiles. Anyways, right? So you have this reaction conditions, right? You have an alcohol, right? You have your base, and you have your, I guess, electrophile in this case. This is one thing I always kind of want to go over and over. Identify the nature of your reagents, right? This is a base here. This is an alkyl halide, so usually that's an electrophile, right? Which means most likely, right, your nucleophile source is going to be your alcohol, right? So even if you forgot the reaction, if you break down everything in a reaction scheme to its purpose, right, whether it's an acid, a base, an electrophile or nucleophile, you'll probably be able to work out this reaction, right? Now, I mean, I've been doing this for a while, so I know how the reaction works, but let's say if I didn't, right? My first logical step would be, okay, I have a base here, I have an alcohol here, the base can deprotonate this alcohol, right? And that's the first step in the reaction. So let's start with that. So now we have Na plus and H minus, right? So this is sodium hydride, right? It's a good source of H minus, which is a very strong base, hydride, right? But it's not a good nucleophile. And the reason why it's not a good nucleophile is because it doesn't have any really, well, yeah, it's not very polarizable, right? And that's kind of what makes good nucleophiles is the charge separation, right? This is kind of a salt. It separates, well, not salt, but it's ionic, right? It's Na plus and H minus, right? Hydride nucleophiles, you guys have seen a source of that before in Orgo 1. Does anyone maybe remember one? You probably saw it in the alcohol chapter, chapter 12. Anyone remember this? Yeah, well, I was just asking if you remember a nucleophilic source of H minus, right? So this is lithium aluminum hydride, or LAH. You've probably seen this in Orgo 1 towards the end of the class usually. But here, the difference here is now you have an electronegativity difference, right? And this bond, right, between aluminum and hydrogen is polarized, right? Which means this hydrogen can act as a nucleophile because there's that charge kind of separation. There's that polarized difference there, right? So sodium hydride, on the other hand, right, it doesn't have that, right? It separates into Na plus and H minus, right? So it can, H minus here only functions as a base, right? So one important thing to always remember when you see NaH, it's always going to be acting as a base, always, right? And that's why you can't use it for like a typical nucleophilic reaction. It's only good for like deprotonating stuff, or like reacting with, I guess, Lewis acids. So anyways, H minus here, right? It's going to, let me actually draw this a little better. So OH here, you're grabbing this, right? So H minus grabs the hydrogen, right? But it's only grabbing the proton, which means the electrons return here, go down this way, and we get our alkoxide, right? So this is kind of where the kind of main thing you're trying to form to do the reaction with, right, is the alkoxide, right? So alcohol, whenever you deprotonate an alcohol, it's called an alkoxide, right? So like if you deprotonated ethanol, it'd be ethoxide. If you deprotonated propanol, it would be propoxide, or etc., right? Methoxide, right? So that's a deprotonated alcohol, or any sort of R group with the O minus, right? And this is a very good nucleophile, right? Because oxygen has that polarized difference between its carbon. It can hold a negative charge really well because it's electronegative, so it will function as a very good nucleophile, right? And that's where the second step comes in, right? And this kind of always happens.
Excuse me?
Mm-hmm.
Yeah, I'm sorry. I'm just asking a lot of questions, but
That's fine.
I want to know, how do you like for this first step, like how did you know that you had to remove the H instead of adding an H to it? Like,
so that's a good question. So like I said, you got to identify the nature of your reagents, right? You know sodium hydride is a base, right? There's probably certain bases, like I said, I hate the word memorizing, but you probably just kind of have to remember them. Sodium hydride is one of them, terbutoxide, ethoxide, methoxide. There's a lot of them, right? But H minus here, right? This is our base, and this is just an alcohol here, right? Essentially, if you just look at the alcohol, you know that the proton in an alcohol is very acidic, right? Because if you remove it, right, the negative charge is stabilized well by oxygen, right? So that's how you knew that if you have a H minus here, this is the most acidic proton, because technically there's more protons all over this molecule, right? All these other protons, right? But the most acidic proton out of all of them will be the one that's on the oxygen, or the part of the hydroxyl group, right? So whenever you have a base and a substrate that has an acidic proton, almost always the first step that's going to happen is a deprotonation, because that's literally what you're doing. You're essentially, you have a good acid, right? In this case, the acid is your alcohol, and you have a base, which is H minus, right? So acid and base, the base is going to grab the most acidic proton off of it, right? So that's how you start with the first step, as opposed to adding an H, right? Because if you tried to add an H, right? Well, you can add an H, right? Because if you think about it, let's look at all the electrons here, right? So if we added an H to this, we're bringing H with two electrons to an oxygen. That's going to give oxygen way too many electrons. It's going to break that octet rule, right? So that's not even chemically possible, right? To add an H minus to something that is already, the octet is already kind of full, right? So two ways to look at it, right? Either you could, identify what each thing is doing. In this case, it's a base and an acid, or you could kind of think about it in the logical way of negative and positive, right? This is something electron rich. This is also technically electron rich at oxygen. You can't add more electrons to an already rich oxygen, right? So we deprotonate it, we form O minus, and then the second step, which did I use? I used that isopropyl iodide or whatever. So next step, let's draw it up here. So right, we have electrons technically. I'm drawing all the electrons here right now, but generally you'll notice for whenever I do mechanisms or anything, I'll usually only draw one lone pair, which is the one that, the arrow movement is happening it. But just remember the other lone pairs are there, right? So it's up to you whether you want to draw all of them or not. If it helps you, draw all of them. If you understand it without it, feel free to, right? So this goes here and iodine kicks off, right? And the second step, what type of reaction is this again? Concerted mechanism, SN2, right? So same thing. It's a deprotonation followed by SN2 reaction. Only difference here, and now this is kind of where this comes into play, right? Was remember the first thing I talked about was acidic media and basic media, right? So if we look at that acid catalyzed ether synthesis, right? We had acidic conditions. Everything here has a positive or a neutral charge, right? The first step was a protonation, which made something with a positive charge. Then a neutral nucleophile attacked, and then it got deprotonated. But nothing here was negative. Now, if we go down here, we're in basic conditions, right? The first step was a deprotonation. It made something negative, reacted with something neutral, and then you get your final product. So those two things, they always come into play if you think about it, right? That's why I like to start off the semester with always kind of iterating those two things. Honestly, I didn't even realize until I just did it that I could use those, because I generally like to use, I always introduce it at the beginning of the semester, but it's much more useful when you get to the later chapters because you see it a lot more clearly in those mechanisms. But hey, it's already applicable, right? So anyways, right, we get this now, and now we form this O carbon bond and we form an ether. So oh wow, it's already 8. That's okay. We don't only really have other thing to cover is epoxide. So okay, we'll probably end up using most of the lesson time. That's fine. Feel free to keep asking questions. Like I said, I don't mind. Okay, so that's our final product, right? Are we missing anything, or are we good here in terms of charge? Negative charge. Okay, so we got differing opinions. So actually we're good, right? Because if you see this negative charge, right? Technically, if you think about it, this is like partially positive, right? Because of that carbon iodine bond, right? So this is a negative species reacting with something that's neutral, right? So it's giving away one of its electrons, right, to form that bond, right? Okay, hopefully you see it, right? It's giving away its electron to form the bond. Therefore, it's losing its -1 formal charge and going back to neutral, right? And what's not shown here, which will probably make a little of this more clear, it's what leaves, and it's probably just kind of chilling in the solution, is I minus, right? So that charge, as someone asked before, right, that conservation of charge, right, it's still happening, right? The negative charge is just on iodine. It's not on our final substrate, right? Charge is always, so in this case, there's no carbocation intermediate, right? Because this is an SN2 type reaction, right? It all happens in one step in this case. So if it was SN1, then you have what's a carbocation, but maybe you or somebody else can explain why we don't get a carbocation in this case. It's kind of important to actually think about. It's good that you question that. Why don't we get a carbocation here? Like instead of this step being considered SN2, what's stopping it from going SN1? Doesn't have to do with the H. Think about the type of carbon it is, right? There you go. There, got it. Well, in this case, it's primary, right? Where that carbon would be. But you're on the right track. I can see why you think it was tertiary because of the tertiary right next to it, but it's fine. No, you're good. But yeah, that has to do with the alkyl groups connected to it, right? And the more alkyl groups you have, the more stabilized your carbocation is. And primary carbocations basically never form. Maybe under certain conditions, and maybe someone's published a paper on it, but for the most part, they do not form, right? They are too unstable. If anyone maybe remembers what causes the stability, it's a word that begins with an H, which is probably going to come up later again in this semester. What gives carbocations their stability? What's that kind of hyperconjugation? There you go. So I won't write it now, but it's going to come up before later, is when you form carbocations or any sort of positive form species. There's kind of, I guess, a phenomenon, if you want to call it, that's called hyperconjugations, where essentially you have electron density being donated into the p orbital. It's actually a sigma p interaction, if I remember correctly, and it stabilizes carbocations. There's also something called negative hyperconjugation, but it's probably beyond what you need to know for this class. That was actually something I learned from Professor Biscoe, negative hyperconjugation. But anyways, that's why I can't form a carbocation. That's why it goes SN2. It's a primary alkyl halide, right? If it was secondary, then there's a chance of it. If it was tertiary, then this reaction wouldn't occur, right? And I was mentioning earlier, right? Why is sodium hydride a good choice of base here, right? What byproduct did I not show? Which is not really important for the reaction mechanism, but it's important to think about why this is, I guess back then, Williamson chose to use it, H2, right? Because technically what's coming out is H2, right? And whenever you form a gas in a chemical reaction, whether it's organic, inorganic, or whatever kind of chemistry you're doing, gases are kind of the best thing you can form because you can literally just have a valve or whatever, and the gas can literally just escape, right? And as I mentioned earlier, Le Chatelier's principle, it'll always come back into play, right? Is if you use sodium hydride as a base, right, you can essentially exploit Le Chatelier's principle, right? Because all of the alcohol present will be deprotonated, right? If you let all that H2 gas escape, right? It's going to form this almost completely, right? And that's why NaH is a good choice of base, or at least used to be, because you're going to get full kind of conversion to your, well, not full, but very high conversion or high yield of your alkoxide, which can then eventually react with your alkyl halide, right? So once again, Le Chatelier's principle is something you could always exploit in reactions, right? If you know there's something you could easily distill or a gas you could form, right? It will push reactions to the right, form your products in great quantity, right? So just the thing to remember is like out of all the bases you could choose, why does the book, why are you taught, and why did Williamson choose NaH? It's because of that reason, because hydrogen gas can be expelled, right? But like I said before, this could be any strong base here, right? As I mentioned here. So let's do some problems where I'll let you guys break down, I guess, kind of, this would be retrosynthesis. Oh, LAH just came into play because I was just talking about the difference between sodium hydride and LAH. Like they're two different types of H minus sources. This is a strong base, NaH, and lithium aluminum hydride is a strong nucleophile, right? So it's a nucleophilic H minus, and this is basic H minus, right? You could use NaOH, right? Yeah, there's nothing stopping you. The only thing is you'll probably have a possible side reaction with if you have to be very careful with the amount of NaOH you use, because technically your OH can react with your alkyl halide, right? So if you have any unused base there, you'll get undesired side products, right? But there's nothing stopping you from using NaOH. It's still perfectly usable. It's just a yield thing, right? Or efficiency thing. But I don't know. That's why the only thing about I wish the book just said just strong base for the first step, right? Because when I did this week, I used terbutoxide, right? We'll actually do that as an example as a bit, but I want to give you guys some breakdown examples so we can practice this. Then let's go over a couple of the other reactions, but I want to make sure I get epoxides covered. So I was hoping to do the molecular orbitals this week, but it's fine if we don't. Okay, let's give you guys some practice problems. So yeah, you could use NaOH, you could use NaOET probably, sodium hydride. But as I mentioned before, let me just while I write these problems, explain to you guys why. So let's do 13.5, we'll do B. So this problem set asks you, show reagents that you would use to prepare the following ethers. So basically, you got to break down the molecule I give you and give me the original alcohol and alkyl halide, right, that you could possibly use to make it, right? So in this case, so we'll do two of them actually. And then we have C, right? So you guys could take like 3-4 minutes to do these. So these are the final ethers, right? OMe, right? And you have to figure out the original alcohol and alkyl halide, right? So you could work on those. But anyways, like I was saying, the reason why sodium hydride is not very a practical base to use, especially with all the other options available now, is it's a combustible base, right? And like I said, it forms hydrogen gas, right? It's a strong base, right? What's present in air that it could form hydrogen gas with? Water, right? Oxygen, a lot of different things it could, well, probably oxygen too, yeah, but I'm not actually sure about that, but mostly water, right? Water vapor in the air that's present, right? So it's going to deprotonate the water, right? Form hydrogen gas, right? If you're just have it kind of lying around, it could, they'll actually then the oxygen, actually no, you need some sort of ignition. But either way, right? It's not safe to work with for that reason, right? Because you're forming hydrogen gas if it interacts with anything that has acidic protons, right? And that's why it comes under use into like kind of a, I guess the terminology would be glove box chemistry, right? Because it's hard to handle under like a regular fume hood or on a bench top, right? Because it's so reactive with, anything that's slightly acidic. You're going to be forming hydrogen gas, and you don't want to blow stuff up because it's going to cause you a problem. It's going to cause your PI a problem, and you're going to have OSHA up your ass. So not something you generally want to use. And if you do use it, you have to do it in a glove box. And for those who don't know what a glove box is, essentially it's like literally a box or a container, right? And that has an inert atmosphere, whether it's nitrogen or argon gas, right? And basically you could store all sorts of reagents and molecules, whatever you have, right? And store them under inert atmosphere without worrying about like oxygen or water interacting with something, right? Most labs have one. We have one. Like most wet labs usually have a glove box. So if I remember correctly, sodium hydride, I'm pretty sure it's not just always stored in the glove box, but it's also stored in like oil or whatever, right? Yeah, probably like mineral oil or something like that. But that's to prevent it from reacting with any sort of residual thing, even in a glove box, right? So like I said, it's an annoying thing to work with, right? Yeah, back then, they didn't have OSHA or any of those safety protocols, right? So my guy Williamson he was taking a lot of risk working with that stuff, that's for sure. But hey, it worked. It's still a practically useful thing to this day. Anyways, hopefully some of you have done this thing. So anyways, let's break this down. So the first one, right, we could go two ways, right? We could either, let's use red, we could cleave it from this side or cleave it on this side. But generally, well, technically in this case, you have both our secondary positions, right? So you could make this two ways, right? So hopefully some of you have gotten this one where you start with cyclohexanol like we did in the last example. The first step is NaH. I always use NaH here because it's just easy to always remember, right? But like I said, any strong base is fine. And then the second step would be the other part of the molecule, right? Which would be this, and then instead of the oxygen, because the oxygen is part of the alcohol there, it would be connected to that X, right? So it would be iodide, halogen. Generally, you want to use iodides, alkyl iodides, right? So that's one way you could do this, or the other way you could have done this is if you started with propanol, right? We cleaved it the other way, right? Then you would, first step is base, second step, so you actually make a line there, distinct this, and boom, you could have used that. So two ways of getting the same product, right? I actually don't know which one would be cheaper. Probably the first one, because cyclohexanol is relatively cheap and propyl iodide is probably a lot easier to make than cyclohexyl iodide. So yeah, two ways of getting the same thing, right? And that's kind of why this reaction is useful, because you could do multiple things, right? You could have you might be trying to create an ether in some big molecule, right? It's like some big synthesis you're doing, right? And you can literally attach R groups to it. So yeah, very useful. And then the other one is oh, I'm so sorry. I missed a methyl group, which kind of changes everything here. Sorry, there was a methyl group there. My bad. But anyways, I'll explain why that makes a difference, because this is a tertiary position here, right? Which means, and once again, we could write this as a methyl group looking like this. So if we cleaved it both ways, right? Both of these can't be the alcohol, right? Because if you tried to use, let's say, methanol, right? So OME, right? OHME, and then this other one would be your alkyl iodide, right? What's the issue here, right? What happens in the second step? Exactly, it's tertiary, right? That second step is an SN2 reaction. SN2 reactions do not happen at tertiary carbocations. So you could actually only make this one way, right? So this would be incorrect. You could only make it one way, which would be, sorry, let me draw it in the other color, which would be using OH, then the first step is NaH, deprotonate that, and then the second step would be methyl iodide, so just MEI, right? Because you need to have your oxygen on the tertiary side, because that's the nucleophile, right? If you made this the electrophile, it wouldn't be a good electrophile for SN2 reactions, right? So yeah, pretty straightforward, I guess, there. Yeah, so if both sides are tertiary, right? So I mean, then you'd probably have to use some other type of reaction, which I don't really know off the top of my head. I don't even know if that would sterically be even possible. Maybe it would be. You have something like this, or really even the same group on the other side. I'm sure there is a probably way to do it. I just don't know it, or maybe I just forgot it. But I don't really recall remembering anyway. Yeah, sure. So the position of the OH, right? So as long as one side is in tertiary, right? The OH, the alcohol can come from either R group, right? That's kind of like nice thing about this reaction, right? Is that you have this variability in terms of what kind of alcohol and what kind of alkyl halide you use, right? So in this case, right, the alcohol can only come from one side, because if we cleave it both ways, right, one way we form methanol, right, which is fine, right? You can use this for Williamson ether synthesis, and the other way we form, like I said, OH here, right, which is also fine, right? But that would mean the counterpart here would be your tertiary iodide here. The counterpart here was the one we showed below, which was MEI, right? So once you deprotonate methanol, right, you get MEO minus, right? And then this cannot go through an SN2 process, right? Basically, this interaction is not possible, right? Because this is supposed to be an SN2 process, right? And you're in basic conditions, right? So SN1 is just not viable here, because otherwise your base would just immediately interact with the tertiary position. So you can't go that way, right? Because the electrophile has to be a good electrophile for SN2 reactions. So it can't be tertiary. It could only be primary or secondary, right? Okay, so we all good on that. There's also the alkoxy mercuration, demercuration. That's pretty straightforward. I think, guess we can do an example of that quickly, because I really want to get to epoxides. That's really the other side of this chapter. I guess I can do one example of that. It's 13.7a, right? So it just asks you to identify reagents that you might use to make this. OET, right? So this was something you learned from Orgo 1, so it's kind of just really a quick review of that. I usually mention this when we go over alkoxy mercuration, demercuration, or I should say, it would be, what is it? No, it would be with water instead, sorry. But yeah, the only difference is instead of water as your solvent, or water as your nucleophile technically, right, you're just using an ROH group, right? So when you guys learned this about, I think in Orgo 1, which is like oxymercuration, demercuration, right? That's using water. Oxy, right? That means there's an alkyl group attached to the oxygen source. So it's using an alcohol, right? Yes, it is a Markovnikov addition, right? So Markovnikov's rule, right, is that when you're doing an addition reaction or whatever with alkenes, is you form the hydrogen goes on the least substituted position, whatever. I hate that explanation. I always think of it as a Markovnikov addition is you always form the most stable carbocation, right? Because there are cases where you form a more stable carbocation on another position that might not be exactly clear, right? So I know the book, and you probably learned it as an Orgo 1, tells you the H ends up on position with more H's, or however it might be. But I like to think of it as when you're doing an addition reaction, right? You're just forming the most stable carbocation, right? Nature just always prefers stability. You'll see that. I mean, really in any science class, nature wants the lowest state of potential energy, right? Whether that's reactions, physics, biology, right? Things are always striving to become stable or lower in energy. So anyways, this asks you just for the reaction set for this. What would be an example or most stable is anti-Markovnikov? Well, it wouldn't be an anti-Markovnikov. It's more I'll talk about it after we do this because I want to make sure we cover everything on hand first. But just remind me after we're done and I'll go over it. I already ate, so I'm fine with sticking around for a little bit more. It's not an issue. Anyways, it just asked you, yeah, so it asked you for the reagents. So the first set of reagents, right, is, what is it? Hg, oops, let's write that a little better. HgOAC 2, right? So H2O, it wouldn't be H2O here, right? Because the difference here is we're making an ether out of this, right? So normally this would be an OH, right? If this was with water, but in this case, it's an ROH. Specifically, it would be ethanol. Let's maybe move this.
I'm sorry, I didn't understand why did we use the ethanol instead of water?
Because our final product is an ether, right? So what we're trying to go for here, right, is an OET, not an OH, right? So if you remember this reaction, right, essentially it goes through something called the Mercuranium ion. I'm just going to draw the intermediate. Should be Hg, right? This would be OAC here. You get formed, you get this formed, right? This is the intermediate it goes through, right? This is Orgo 1 review, but this is called the Mercuranium ion, right? It forms with that mercury acetate there, right? This is positive, right? And now you have this kind of three-membered species here. You're going to see this is very partially positive, right? Because it can stabilize a positive charge much better than the other position, right? So if you label this as partially positive 1, this would be like plus, right? This can stabilize that positive charge better because it has more alkyl groups. So through hyperconjugation, that charge is better stabilized, right? So now what happens, right, is the nucleophile in the regular reaction you guys probably learned was water, right? So that would be OH2, right? That would come in, attack at the more stable or more positive position. He gets kicked off, right? And essentially you get the next intermediate that would look like, after deprotonation, it would look like this, HgOAC or whatever. And then the second step is the demercuration step, which the mechanism, pretty sure it's a radical mechanism. I'm not sure, but it's not covered in this class and not something you need to know for undergraduate stuff. But essentially all that does is it removes this and turns that to an H. Actually, I don't think it is a radical mechanism. But anyways, it's not something that you don't need to know the mechanism of. The first part of this reaction, you guys learned in Orgo 1, right? So that's why I was quickly reiterating that. But now in this case, right, that would give us a product that looked like this, OH, like that, right? That's because we use water instead. But we're trying to get OET, right? Which means the original source has to be ethanol, right? And instead of water now, we're going to have ethanol. Electrons would be coming from here, right? Coming and attacking there. And now over here, we have OET, right? Because that's a nucleophile. You have your HG attached. Second step with sodium borohydride, mercurates it, or however you want to call it, right? So two-step reaction. Only difference from what you learned in Orgo 1 is instead of H2O, now you have an alcohol you could use, right? So if I use methanol, the final product would be OME. I use propanol, butanol, etc., right? It would be O and whatever R group is attached, right? So that's how you would do it. That actually makes me...
What did the second step do, the NaBH4?
That removes the mercury off of it. So after the first step, essentially you get a product that looks like this, right? So that's the result of just the first step. When you add sodium borohydride, it just removes this HgOAC group and installs an H in there. So that's the second step. That's what I was saying, the mechanism of that. It's not really something you need to know for undergraduate organic chemistry. And I don't think it's really even covered, but I'm pretty sure it's a simple, it just probably delivers hydride at that position. I just don't remember how it interacts with mercury. But the second step, literally all you need to know is it just removes the HgOAC, right? The first step creates that. The second step just removes it. Them two together get you that final product, which is just OET here. If it was water, it would be OH, right? So That's really the only difference from now and from what you learned in Orgo 1 is all we changed was water to alcohol, right? And it literally changed the entire product, right? From a alcohol to now an ether, right? If you want me to draw out this OET group, right, it would just look like this, right? Because that's ethanol. Maybe that's a little bit more visual, better visual there when you draw out the full groups, that you're making an ether as opposed to an alcohol. Okay, what else? I think this acidic cleavage is left, and then we'll take, whatever, we'll just continue on, it's fine. Yeah, acidic cleavage is just basically one of the reactions of an ether. Basically, you could break down an ether, right? If you just introduce it to, generally it's a halo acid, right? So something like HCl, or I guess HBr. Generally, it's just HCl. Probably hydrogen iodide too, but anyway, so if you have an ether, right? So those are two ways to make ethers, right? If you have an ether, so yeah, let's do an example of this. Which one of these do I want to do? Do F. This is 13.10 F. Now I just realized I picked another example with the cyclohexanol. We'll do one more. Just anyways, so you have excess amount of excess. In this case, they said HBr, and you just need heat. So heat is also represented by this delta sign. So if you ever see me or you ever see Professor Pisco use that delta sign, all it just means is there's heat, right? So what this does, right, is when you introduce acid to it, right? We'll do the mechanism for this as well. So let's draw it out like this: HBr, right? Yeah, one pair of electrons, right there. So this has electron rich, right? This is a very strong acid, right? And the electrons on a ether can get protonated, right? Or I should say the oxygen in an ether can get protonated if it's a very strong acid, right? Because this proton essentially wants to leave this Br anyways, right? So now you get a protonated ether species or whatever you want to call it. So in this case, you could technically get two products, but we'll just do one for now. Now you have OH plus, right? Okay, now you have two things happening here, right? Is you have two positions here, right? Technically, both these carbons are slightly electrophilic, right? Yeah, it would be better to cleave it this way. Sorry, I was just kind of thinking about it for a second. So now let's take Br, I guess is floating around, right? So you have Br minus, right? Well, it's going to happen twice, so it doesn't matter which way I go first. So I'll just pick the right side since it's closer anyways. So Br is going to come. It's going to attack at this position, right? It's going to cleave off here, right? And now you get what this would be. This would be ethyl bromide. So you have ethyl bromide there, and then the other part is a cyclohexanol, right? But it doesn't stop here, right? There's a specific reason why it said an excess amount of HBr, because you're going to turn everything into an alkyl halide, right? And remember, this is an alcohol, right? You have an alcohol in an acidic environment, and there's a lot of energy present, right? So it's going to take another molecule of HBr that's probably just floating around, right? Let's take this here, OH group, right? O oxygen electron rich. You have a very strong acid, grabs a proton, right? Kicks it off. Now you have this oxonium ion, OH2 plus. That's a good leaving group, right? You have a Br minus floating around, right? Br minus, good nucleophile. And then it's going to come in here, kick off water, right? And then boom, you get 2 alkyl halides as a result. So it would be this. So your final products would be this plus the first one you did, right? So that's why I use an excess amount of the halo acid, right? It's just going to cleave it completely until everything is an alkyl halide, right? And then what's kind of left after the end is just water. Oh yeah, so technically I should write water, but you don't really have to include that. The main thing usually if you see a acidic cleavage is they just want the 2 alkyl halides you get as a result of it, right? So yeah, that's acidic cleavage, and I think that's probably the only other reaction with thing as far as I remember. Anyways, we can get into epoxides. Okay, 1 second. I'm sorry, I'm just looking through in chapter problems. So generally I like to go over the in chapter problems so that way you guys can practice the end of chapters yourselves. Just kind of looking through which ones I want to do. Okay. Zoom in here. So epoxides. All right. So epoxides, as you guys probably learned, they're 3-membered oxygen rings. They're kind of a cyclic ether, if you think about it, right? They are still technically an ether. That's an OR, OR on each side. They're just a very specific, special type of them. If you guys ever heard of epoxy resin, right? That's generally where it's used. If what is it? Mm-hmm.
I want to just go back to the previous question, just the end. We weren't trying to make an ether, right? What is it in the end?
We're breaking down an ether, right? So maybe I should have wrote it, sorry about that, but acidic cleavage, right? So we're cleaving the ether in here, right? So the other 2 reactions were synthesis of ethers. This was a reaction of an ether, right? So in this case, it was if you used an ether, if you reacted it with a halo acid, you would just break it down, right? So the first 2 things we learned, which was like the acid catalyzed reaction and the Williamson ether synthesis, those were like, I think the book likes to call it preparation reactions, right? And this is a reaction of that specific functional group. So here, this first starting material is an ether, right? This is cyclohexyl group, this is an ethyl group. We introduced it to a very strong acid environment, HBr. So all that what happens is just a series of kind of protonations and nucleophilic attacks, right? First thing happens, the ether got protonated, right here, right? Then a Br minus attacked one of the carbons that formed one alkyl bromide. In this case, it would be ethyl bromide. Then you had what's left over would be the alcohol, right? Once again, you're in an acidic environment, right? You have an excess amount of your acid, right? Now your alcohol can get protonated by the acid, right? And then the bromide can attack that position again. And essentially you get, these 2 products, right? 2 alkyl bromides. So if I wrote a general scheme, it would be R, O, R, R prime. Could call, actually we'll call the other one R prime.
And what was the purpose of the heat? How did that?
You just need enough temperature to do the reaction, right? It's kind of just like, if you had it at low temperature, they would just kind of be sitting around. But when you heat it up, things are moving faster, right? You're increasing the kinetic energy, so it would react better, right?
Like I would just have to know that. Like these are like little knowledges that I would have to know. Like I would need to.
Yeah, I guess in this sense, I mean, you probably would, if you wrote this on, like if you're trying to use acidic cleavage on an exam, I think if you wrote excess amount of, HX, whatever that HBr, HCl, whatever acid you're using, it'll probably be enough, but it's just a little thing. The book I know mentions it. I'm pretty sure he probably mentioned it too, but it's just, yeah. You'll probably be fine without writing it, but it is technically needed in the reaction. And one thing to note about all these reaction schemes you guys have been seeing through Orgo 1 and now Orgo 2, this is not how you would publish it in a paper, right? Because in a paper, it's much more detailed. It tells you the exact temperature and like every little detail. So like these are very generalized schemes. So for the most part, like I think Professor Biscoe is pretty lenient when it comes to the partial credit anyway. So for something like the delta sign or the heat, you probably wouldn't take a point because he knows you understand the chemistry, right? But it's just little things like that. But yeah, in a paper they tell you the solvent, the temperature, all the reagents, the equivalence of the reagents or the mole percent, right? So this is all stuff is like still very like I guess low detailed compared to what's actually published in actual journals. But yeah, like you said, it's just a little thing, but it is technically needed to start the reaction, right? Need things at a certain temperature moving because at room temperature it would just take forever basically. Probably could still happen, it would just take forever. Okay, epoxides. Let's see where we could start with epoxides. We're probably gonna have to bring this into the next thing, but that's fine. We'll figure out where do I want to start with. Did he cover sharpless epoxidation? I would assume he probably does. It seems Professor Biscoe is like, our group mostly does organometallics, so I wouldn't be surprised if he did. Did you guys do an antioselective epoxidation using like sharpless catalyst or whatever? Oh, you didn't? Okay, well, better for you guys. I just want to make sure because I was just like quickly looking over the chapter to see where to start. So, okay, we'll just start with basic epoxide reactions then. Let's see which ones. Okay, so preparation reactions, let's do 13.13, right? So once again, to reiterate, epoxides are this, right? 3-membered oxygen ring, right? You could have other R groups here, right? Nobel Prize in Chemistry, I think 2000 or 2001, Sharpless. Well, he got it for epoxidation, and I think Noyori and Knowles got it for asymmetric hydrogenation. But essentially, like this work is still pretty useful, right? And epoxides, like I said, are very useful. They usually see them in like something like epoxy resin or whatever, which is like polymerized, like long chain polymers that have a lot of epoxide groups and usually some other big R group, right? Stuff like, I don't know, well, epoxy resin you use in arts and crafts or like, woodworking or, coating something with it. Probably glues or like other sticky residues have epoxide groups in them. It's very, I guess, commercially important group. And I don't know too much about medical drugs that have it, but I'm sure there are probably biological molecules that have it too. Anyways, let's do B. Start with something a little easy. So this is asking you reactants that you would use to form. Says racemic mixture, but let's not really worry about that too much right now. But really, how would you form the certain epoxide? So we're going to start off with this one. Yeah, we got to make a little space here. Man, they really like their cyclohexyl groups in this. So here you have this H. You have H here, and this is a methyl group, right? So basically, it's asking you to kind of work backwards. Is how would you get this sort of epoxide? And there's only 2 ways that, as far as I know, that you guys learned how to make epoxides. Can anyone mention both those ways?
Is one via MCPBA?
Yep. So one MCPBA, yeah, or any sort of peroxy acid, right? MCPBA is what metachloroperoxybenzoic acid. But really, it's any peroxy acid group that could do it. And the other one is something you probably learned in the addition reactions as well.
Halohydrins.
Yeah, halohydrins. So close there, Ahmad. It's bromine gas with water, right? You form a brominium ion, then using the brominium ion, you form a halohydrin, right? And then you deprotonate that halohydrin, kick off the Br, and you get an epoxide. Pretty sure that's how it would work, yeah. There's we probably won't have time to do it. I would assume he probably covered it in class, but like probably like showed you cyclohexanes or whatever, like alkenes in a cyclohexane using the brominium ion, because the kind of location when you do that second method is very important, right? Because if you have it like in a, what's it called, equatorial versus axial position, in certain positions it wouldn't happen. I would assume he probably covered it. I don't think I have an example to cover that here, but it is important knowing the kind of how in 3D space, how it works, right? Maybe sometime later before the exam or whatever, I'll go over an example of that. But for now, you just kind of need to know how you can make this, right? So if we went back, right, this would start from an alkene, right? So we could start the alkene here, right? And then on one side of the alkene, right, you have your cyclohexyl group. On the other side, you have the H, right? And then on the other side, you have an H and Me. So in this case, it would be H and Me, right? One thing to notice though is kind of the positions I put the Me and cyclohexyl group. They're opposite to each other. Anyone maybe think why I did that? Or I should say they're trans to each other. In this case, it'd be like E to each other, right? Well, it has to do with the location on the final product, right? So whether the alkene is cis, trans, E or Z, whatever descriptors you want to use, right? It affects the location on the final product, right? So if you notice, right, let's use a color here. This is on a dash and the methyl group is on a wedge, right? Which means they would have to be opposite to each other from the original alkene, right? Because however, now when this epoxide forms, let's draw like this O here, right? It's kind of bad, but essentially when we're trying to form the epoxide, right? Them being opposite to each other would means the original alkene, they'd have to be opposite to each other, right? So kind of taking note of whether they're on wedges or dashes is very important when you're doing an epoxidation, right? Because it affects the final product. So when you have cis alkenes, 2R groups will be on the same side. When you have trans alkenes, they'll be on opposite sides. So same side would mean they're either both on a wedge or both on a dash. And then opposite sides is obviously one is on a dash, one is on a wedge, right? So the original starting alkene, right, would have to look like this, right? It would be a cyclohexyl on one side and methyl on the other side. Other two are hydrogens, right? If you want, you could probably erase this, make this a little better drawing. So let's actually do that. So, sorry, let's keep the same color. Me group, right? So we have a trans alkene here, right? Or E, I guess, right? And now you could use two sets of reagents, right? You could either use MCPBA, right? You should ask him. I mean, I would assume since people already mentioned MCPBA, right? If you could also just write it generally as RCO3H, yeah, that should be it. This is any kind of peroxy acid. The R group can be like an ethyl, phenyl group, whatever it is, right? The main thing is where when you form that epoxide, I'm not going to really go into details on it now, but maybe sometime later if someone wants to review that mechanism, we can. But you just need this kind of molecule, right? Because all the chemistry is happening between this and the alkene, right? So that's one way of doing it, right? And then the other way of doing it would be through the halohydrin, the Br2, H2O, followed by your base to deprotonate it. Oops. But generally, you don't want to use halohydrin formation because bromine, very toxic gas, right? There's one thing like I try to like incorporate like why, we use certain methods over other. I mean, both are fine, I mean, people discovered both so people could use both, right? Alternative routes should always be, explored and learned about. But like, these days, especially, people try to focus on greener chemistry or more practical chemistry. Bromine gas is just not something you want to deal with or inhale, right? So while it is a possible way to do it, it's not something you would want to really do today. And you'd probably need probably have to do it in a glove box for sure. You could probably work with it in a hood. You just have to, like I said, you have to make sure. I mean, everyone's wearing a face mask these days, so just make sure you're masked up and you have like your hood down or whatever. But anyways, the key thing with this example was knowing the trans, that the original alkene had to be trans, right? Someone gonna say something?
Yeah, how did it go from the first step to the second step? Like we just have the arrow, but what happened to make it like turn into that?
Sorry, I should maybe remove this.
From the side to the trans structure.
Sorry, so this is a retrosynthesis arrow, right? This technically the reaction scheme would look like this. 1 second. Let's see if I could copy and paste this thing. Right, so the reaction scheme would look like this. You start from your alkene, you use either, you actually make this a little less confusing. You could either use MCPBA or the halohydrin method and you get that product, right? What we originally did though was a retrosynthesis to kind of, because we know epoxides come from alkenes, right? So we had to work backwards, and the main thing you had to identify was where the two R groups were going to be, and they were going to be opposite or trans to each other, right? I don't know if he asks questions where like if he gives you a product and asks you to how would you create this. Usually he'll give you something like this, where if he'll give you like this product here where I drew this arrow, right? And then he'll give you a reagent set, right? Whether it's MCPB or A, and then he'll ask you for the product, right? So really it's the reverse of what they're doing. I think the book likes to do the other way around, but like you still get the same point across because you need to figure out how to do it, right? But if you look at the old exams, usually it's question 3, which has 8 specific, like 8 sub questions or 8 parts, whatever you want to call it, 8 reactions, I should say, right? It's usually like, let's say molecule A reacting with C, D, B, C, etc., right? And then you have to figure out the product. That question is usually always worth 24 points. It's 8 reactions in that question. And that's why knowing the reactants, knowing like the reagents, reactions, and all that stuff is important, right? I mean, like I said, depends on how you do it. I try not to memorize stuff. That's what works for you. Great for you. But it is a big portion of your exams is knowing if you're just given a substrate and you're given a set of reagents, do you know what comes out of it, right? So now this question was kind of posed in the opposite way, right? We had the product. We had to figure out the original reagent, the original substrate and reagents we used, right? In this case, there's 2 methods we could have do it. But just for your information, and because that's what's going to be on your exam, I know from experience that your exam is going to be this way, right? Where he's going to give you a substrate, he's going to give you a set of reagents, and he's going to ask you for the product. And they're all worth 3 points each. And there's 8 of them usually in question 3. That's a 24-point question. So why knowing like the basic reactions is very important, right? During the recitation, obviously, since we have time, I like to do the mechanism and stuff. I mean, this one I've kind of usually on the first or 2 recitations is when I kind of get my timing straight because I, figure out who's asking questions or whatever. But like going forward, I'll make sure like I finish every chapter within that recitation session. But like I said, people who's had me before know I don't mind going over because I like to make sure everyone learns properly. That's why you're here, right? That's why I'm here to teach you. So yeah, just the thing for your exams. That's how your exams are gonna look. I just know that from like, that's how Professor Bisco, he does it, right? So each reagent builds off from one or the other. So you know what? Let me show you guys an example of that. we're probably gonna stop around here for epoxidation because I don't really want to rush the rest of it, because the second part, the reactions of epoxides, we'll probably cover next time. I'll probably just host another session earlier. I mean, the thing is, I mean, like today I didn't go to the lab because I finished my reaction yesterday. I'm gonna do the second part tomorrow. But I'll figure out like an hour or two to do that. But we're gonna start normal recitations next Saturday. This weekend I'm busy on both Saturday and Sunday. So normally that's why I like doing it during the afternoon on Saturdays, because usually I'm doing something in the nighttime. Right? But today, this weekend, because I guess COVID or whatever, one of my friends is having a wedding, and the only time they could get is the afternoon. It was like first time I ever been to an afternoon wedding. That's crazy. But yeah, normally I like going like a little bit longer so we do everything. So for that 24-point question, let me give you guys an example of that you could probably actually solve right now, hopefully. Give me a minute. Let me post an example. Find one of these. 2014. Oh, oops. Here we go. Oh yeah, no, it's question 3 or 4. It's one of the questions. I shouldn't say it's question 3 always. It's one of the questions. It's 24 points. It's always going to be on the exam. Okay, so here's one. Let me see if I could. Actually, I'll just post the entire question so you understand what I'm talking about here. Copy and paste this thing for y'all. Let's paste this. Okay, so yeah, next, probably just send out an announcement or whatever, or otherwise we'll just continue at the next recitation. But I kind of want to make sure I get to chapter 16 on the next recitation, so I might just host a session before that. Okay, so hopefully you guys see it here, but oops. This is a question that will be on your exam. And this old exam, it was question number 4. But yeah, that's one of the questions, how it's going to look. It's 24 points, right? There's 8 specific reactions, right? You're given a substrate, you're given the set of reagents, you're asked what it does, right? So yeah, that's why knowing all these reactions is going to be very important, because that's a big chunk of change, right, for your exam. In this case, for this, yeah, you don't have to show mechanism. You just have to show the final product, and specifically the major product too, right? So that's why knowing the entire, that's why I like to cover the entire outcome of the reaction, right? Like you saw all those little side products, those aren't important, like H2O, Br minus, whatever. The main thing is the main products. But sometimes you might have 2 major products that are equivalent or whatever, right? So just be very careful. That's why it specifically says the major products. Or, I mean, this is kind of old, it's 2014, but sometimes he said, this might be written differently. It says, or write NR if no reaction occurs. So that's also an option there, technically. I'm pretty sure the recent exams have this, but there are some cases where, like, you know, you might try to work up a product, but maybe that reaction was just never meant to work out, right? So it's kind of like a trick question in the sense that it's not really a trick. It's still, you need to understand what you're doing, right? So if you understand the chemistry properly, you understand the reaction properly, you will know that, okay, wait, these 2 things, no, they don't do anything together, right? So then you could write NR, right? You'll probably see that in the more later exams that he's made. Let me see if I find one. 2018 exam. Right, yeah, it says predict the major products of the following reaction, write NR if no reaction is expected, right? So like I said, just one of those little things you need to, not really little things, it's just one of those things you need to know. It's not a really unlimited reagents. This is why I probably said this multiple times already, but identify the nature of your reagents. When I took the class way back when, right, I didn't memorize any of this stuff, right? And like when I studied with my friends or whatever, we went to like library and like we did study groups or whatever, and like everyone was trying to memorize. I was like, listen, man, most of these things you already saw beforehand, right? Why am I memorizing this? I just know what it does in this specific case. That's all I need to know. Then I draw. Listen. But yeah, no, because it's like I hate memorizing stuff, which is funny because a lot of like, you know, organic chemists pride themselves on their memory and stuff, which is awesome. You need to know a lot of stuff. But I always was a firm believer in that if you know the logic, you know, like the basic idea of what's happening, you don't need to know everything about it. Okay, I shouldn't say you don't need to know. You don't need to memorize it. You can just figure out what happens, right? Like logic, it's all man. So that's what I'm saying. I guess, I mean, I always loved chemistry and I always loved Orgo. So for me, I could see the logic behind it. It's hard for me to explain. Like that's something I explain a lot better when I'm teaching Orgo 1, like the logic behind it, because that's when you're first learning. So I could like kind of drive in those principles to you. But like, you know, everyone learns differently. Everyone studies differently. It's just how the world is, right? So anyways, we're going to end on this note for, I guess, epoxides. I'll probably either schedule another session or whatever for the rest of this chapter, or I'll just start on next Saturday, which is the 18th. I'll probably end up doing it next week if I'm not too busy, because I'd rather just do it separately. But yeah, for those who want to stick around, ask any other questions, feel free to. Yeah, so that's a good point you brought up there. Well, he recycles the reagents. That's the thing. The reagents, right? Like the stuff above the arrows, right? Those haven't changed for years, right? Some of those have been like this, the Williamson ether synthesis that has literally been around for almost 200 years, like 180 years, whatever, right? That stuff never changes. What's going to change is the substrate, right? So that's why I was saying, like, if you know what those reagents do, then it doesn't matter what that, like, what this, like, this is, or this is, or this is, right? Because you'll know what the chemistry is happening. Like, you know what is occurring between those two things. The rest of the molecule, the rest of the structure is kind of irrelevant. That chemistry only occurs on certain atoms. Right? That's how I've always approached organic chemistry. So if you can localize where those like reactions are occurring, the rest of the structure, it's just there, right? Different structures do different things in that regard. Like you're maybe creating some molecule that's medically important or whatever, for whatever reason, right? But the chemistry is always happening at certain positions. If you could learn that, you'll be good to go, right? So in this case, the first reaction here, something called Friedel-Crafts alkylation, this one. In this case, director, so I already know the product is going to be TBU like this, right? There could have been so many other groups, right? I mean, when we learn this, right, I'm gonna show you like tips and tricks how to do this better, right? Plus signs in this case. So this is a Diels-Alder reaction. Yeah, this is a Diels-Alder reaction. This just means this plus this. So this combined, these two are both substrates, I guess, right? Well, when we get to Diels-Alder, I'll tell you to ask him if he'll accept it, because technically, so this is something called S-trans, right? In this formation, technically, this is one of those questions where there's no reaction that occurred, but usually he expects you to basically turn it like this way. So where is it? Basically wants you to probably rotate it this way and then do the chemistry. But you could technically argue that as that molecule is as is, right, there's no reaction that occurs. And you're going to learn this probably next week when you do Diels-Alder, or tomorrow, actually. Tomorrow's Thursday. Yeah, tomorrow's Thursday. So you might learn this tomorrow. Yeah. So yeah, if there's any other questions, feel free to ask. I'll stick around for a bit. Or anything we covered, or maybe anything thing. But yeah, like throughout the semester, no, that's something you're gonna learn in chapter 17. You haven't gotten there yet. Aromatic, anti-aromatic. Let's see if we have something. It's probably in the review sheet section. I had one semester. Aromaticity. Yeah, so if you go, that's why I say to go through my old notes. This is probably the neatest I've ever wrote something. I always look back at this one sheet. I've never written this, and this is still pretty bad handwriting. But yeah, like I have these review sheets and stuff from my older semesters that you could probably go back to. Yeah. Let me post the link for you in the chat. So what other questions were there? You have like a list or old notes of what each reaction does. There's this one person in our class who we actually studied with, Elizabeth. She had a OneNote notebook that was pretty good, but I don't have it anymore. Well, I do have it, but it's like, I don't know why it's like incomplete. I think the way it's synced, I messed it up or something. And someone asked about the tricks. Yeah, throughout the semester, I'll just show you little ways. So like one example of like a trick, because I was viewing your old lecture there, right, is you guys just learned about molecular orbitals, right? These things, like I said, I am horrible at drawing this, right? You probably have learned this or seen this, right? Terbutyl chloride in that case is a, what is it? It's a yeah, it does function as a nucleophile in that case. Yeah, because it's Friedel-Crafts alkylation, which means the aromatic ring in that case should be functioning as your. Actually, no, in that case, it will probably be a electrophile. Trying to think. Yeah, okay. So your aromatic ring will be like this. You have electron density on it. This is gonna donate this way. This is gonna kick this way, and essentially this ring will grab the terbutyl group. Then it basically, when we get to this in probably in a few weeks, right? You're gonna see basically this charge is gonna delocalize around the ring, right? You get a positive charge here, delocalize around the ring. Hydrogen comes back, closes the ring, regains aromaticity. Get your final product. That's something called electrophilic aromatic substitution, which is a basic basically your what's it called? Aromatic ring is going to always function as one way. So in this case, Tbu chloride will be an electrophile. Your aromatic ring will function as a nucleophile, and you're going to see like 8 reactions. I think 8, maybe 6. I don't remember. Where the aromatic ring in all those cases is a nucleophile, and your electrophile is one of those reagents, right? Like I said, I don't even remember all of it exactly, but I just thought about it logically then. Looked at TBUCl, I was like, okay, wait, no, that's probably electrophile. This is electron-rich nucleophile, right? So like, I don't know. I mean, that's why I never wanted to become a doctor, like a medical doctor, is because I hate memorizing stuff. I'd probably kill one of my patients because I'd be like, oh, does he need codeine or does he need Tylenol? Anyways, so the molecular orbital stuff, right? The reason I brought it up is like one of the things I'll show you next week is a good way to always remember it. You guys learned about how like if you have 4 orbitals, right? If you have a system that looks like this, right? 2 pi bonds, right? You have 4 orbitals here, right? There's 4 molecular orbitals, right? Which each one has 4 p orbitals, right? The lowest energy one has 0 nodes, and you have 1, 2, and 3 nodes, right? This is where wave property comes into play, right? Because a very easy way of drawing this diagram, which you probably did in class, right? Probably did this, right? The first one, they're all, oh my God, that was horrible, that last one, but they're all in phase. Then this has 0 nodes, right? The next one has 1 node, right? And all the way up to the 4th level, because you have 4 molecular orbitals, right? And this is all symmetric, right? Got, I think it's probably C2. C2 is 180, C3 is 120. Yeah, so it should be C2. Anyway, then you have a node here, right? And then you go up and up. But one way to think about it is waves, which is actually what I learned later. It's a good way to always kind of draw these orbitals. Think of them as a wave with nodes in it. This first one has 0 nodes. Second one has 1 node. The third one has 3 nodes. And then you're going to see orbital, 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 right? The next one, and you just keep drawing a wave with nodes. And you could, like, I'd never memorized these diagrams. I just start with the first wave, everything is in phase. Second phase, half are in phase, half are out of phase. The next one, there's 2 nodes. So once again, due to symmetry, 2 are in the middle, 2 in the bottom. And then the last one, which is 1, 1, 1, 1, 3 nodes, right? So I'll show you this in more detail, but like this is one of those like little things that I always kind of use. The link for the OneDrive. Let's see. Let me get that right now. Okay, any other questions chemistry related? Anything from Orgo 1 that somebody might want to review, or something about mechanisms or reactions? Feel free to ask now, because once we start getting the next few chapters, you're gonna fall behind if you don't kind of remember that stuff right now.
I have 2 questions. So first, I feel kind of in like lost in the woods when in lecture, and I've been trying to catch up. I seem to have forgotten a lot of things over the summer. I was just wondering if you had any general guidance on the most efficient way to catch up.
Well, one thing would be the Orgo second language book, which would be the fastest way you could kind of read briefly about all the stuff from Orgo 1, right? Because it's much more condensed, right? You could also view my, one of the winter or summer recitation sessions app, because those classes are a lot more faster paced, right? So like there isn't like 15 recordings you have to view. Let me actually look. I think I have, yeah. So I have 2 actually. You could do summer 2020 or winter 2021. And those are very condensed lessons I have, right? That kind of cover all the Orgo 1 stuff. But reading wise, the best thing I would suggest, like to quickly catch up, would be the second language book, the first semester one. Let me find that OneDrive link. Give me a second. Go to announcements. There we go. Whoops. Shoot. Copy link address. There you go. That should be it. Yeah.
Thank you. I appreciate that.
Yeah, no worries.
My second question is a little more abstract. I did the Orgo second language first semester, like as a way of catching up, but it kind of glosses over why SN1 and E1 reactions don't happen with primary carbocations, and it sort of alludes to like the stability of the cation isn't there, which means the reaction doesn't go forward, which seems counterintuitive to me, because I think of something unstable as being more reactive.
No, that's a good point you brought up, because I actually remember I had this when I had, was it Professor Balling there? Rest in peace, he passed away. But I thought the same thing, because like you learn this like, what is it? That when you have something more reactive, right? I mean, when you have something high energy, it's very reactive, right? So why wouldn't it want to go through a reaction? It has to do with energy diagrams, or really the energy of that reaction, right? In order to get to that highly reactive state, right, you start with your starting material, right? You put a certain influx of energy, right? To get to a primary carbocation or whatever, that activation energy is significantly higher than whatever the activation energy of any other pathway will be. So to get to that position where it can be a primary cation, it would just require so much energy, right? So you can't ever really reach that reactive species, right? It's only kind of
the stability is like equivalent to activation energy?
In a sense, I don't want to like completely relate it, but it's more to reach that kind of species or that like intermediate or transition. So in that case, it would be an intermediate. It would just require a tremendous amount of energy from going from your starting material to your thing. But like if you manage to get it, yeah, it would instantly react with any sort of nucleophile or base or whatever it might be, right? It's just that it requires too much energy to form, so it never forms, right? That's kind of the issue, right? And that's why you don't get primary carbocations, because if you had, let's bring up an example of this, right? It's if you had, let's do something like this. Yeah, let's do the SN1 first. Make this a little simple, right? So if you had this, what is it? Isopropyl chloride, right? You had this, let's say you put up enough heat, right? You cranked it up to like 500 C, right? And you're like, okay, I have enough energy to basically kick off this leaving group, right? And then you're like, okay, boom, I form my carbocation, right? So let's say even if you get there, right? Remember, it's a matter of time, right? And the thing that could happen here is that before this even reacts, right? Because this is all happening at like that picosecond, almost femtosecond scale, right? Even if you manage to break that energy barrier, because going from this chloride to this primary cation, it would require just so much energy. You would probably not be able to physically do it in the real world, right? And even if you did, it would almost within instantaneously have an hydride shift and automatically make it a carb, because the molecule itself would just rearrange to get to a more stable intermediate state, right? So yeah, briefly, maybe like that's the thing. It'll probably be in very trace amounts, and I'm not even sure. This is something I'll ask Professor Bisco about. You might see, like, let's say you had some nucleophile there, right? You might see trace amounts of this product, right? If it went through an SN1 pathway, right?
If it was a strong nucleophile, you wouldn't have to have this conversation. It would just
it would just go SN2, exactly, right? But let's say it was like a weak nucleophile, and maybe you'd have trace amounts, but it's just that even when it reaches that state, it just so quickly, like the shift occurs, that it'll just go back to a more stable state. Because remember, this is all happening with it's faster for it to do a shift than it is for another molecule to actively collide with it. Because that's kind of the underlying thing with chemistry in general, which is, I always think about, like, this is kind of like, because like I want to get into computational chemistry, and a big thing with computational chemistry is orbitals, wave functions, right? And if we could properly like mathematically define them, that's going to be like a great way to do reaction predictions or even optimization for reactions, right? So the kind of issue here is like the time scale that this happens in, we can't really measure it properly, right? So an intramolecular shift will occur faster than another molecule that can actively collide with it, right? So if you remember from, I don't know if it's Chem 1 or Chem 2, you guys learned about effective collision theory, right? Effective collision theory basically states that molecules need to like interact in a certain state, in a certain defined manner. Like it goes from once, like it has to be in a specific like kind of like place in space, and then the other molecule has to attack from a certain side, right, to have an effective collision. That creates a brief transition state, and that eventually causes a reaction, right? So getting that is not simple, because remember, when you have the energy that high anyways, things are just moving so fast anyway. So you getting to react that nucleophile, it wouldn't be as easy as you think it is, right? But I get what you're saying with like, it's more reactive. Why wouldn't it instantly react? It just comes down to like our idea of processing stuff when we write it on pen or paper, right? We think like, okay, it should instantly be able to do it, but like it's happening so fast, it would change to something more stable faster, right? And if it does react with something, it would be such small trace amounts, right? And then the thing that I mentioned before was it would just require way too much energy to even get to that state, that you can never get to that reactive state, right? And a fourth
Thank
thing,
you. I appreciate that.
no worries. And then the fourth thing I'd mention is that If you think about SN2, right? This is why I wish they covered molecular orbital theory a little bit better. It all has to do with homo-LUMO interaction. And you guys probably just learned about this for the first time. This is why I don't get why it's this one of my biggest like kind of complaints about the Klein textbook is it's talked about a little too late. It's talked about in chapter 16 here, which is molecular orbital theory, right? And you learn about homo-LUMO interactions, and that homo-LUMO interactions and like if you understand that stuff properly, you'll understand why reactions even have in the first place, because those are the molecular orbitals that are interacting between molecules. And maybe if you remember from like SN2 reactions or whatever, like what is it? The LUMO of your electrophile is I guess very high in energy, and the HOMO of your nucleophile, right, is going to be very electron rich and the highest energy level, right? So that's why they interact with each other, because it's the electron rich molecule, the nucleophile, has a very good HOMO, and the electron poor electrophile has a very low energy, LUMO, right? So that's why I wish molecular orbital theory, and if I maybe if I have time, I'll talk about it next lecture. But when I learned about that for the first time was when a lot of this stuff started clicking, why things interact the way they do, right? And it all comes down to the orbital interactions and effective collisions and stuff. Can things orient themselves in the proper way for a reaction to occur? And most of the time you can't. That's why you get so many reactions that are published that don't have good yield, because you just, there's only a certain amount you can get to. Like, it's just how it is, right? And that's what computational chemists are working, is how can we like mathematically, I guess, define that using like orbital sets and all these computational methods, right? So we could predict reactions in computer. Because like technically we have the technology to predict reactions, or we're almost there, but we just don't have the proper, I guess, math or definitions for it, right? That's why HOMO and LUMO, the stuff you guys probably maybe covered right now or are about to cover, I think it's some of the most important stuff you can learn in not just organic chemistry, but chemistry in general, because it describes how things interact at the orbital electron level, right? Sorry for my rambling.
It's all very interesting. It's all really interesting, in terms of like scheduling moving forward. Like I have plenty of time this semester, and I'm really looking forward to learning as much as I can about organic chemistry.
That's awesome.
Yeah.
But like I said in my email too, for those who are coming on campus or whatever, I'm like usually there almost every day Monday, but I think going in the future, I probably won't be there on Thursdays. I mean, tomorrow I will be, because I need to make a certain nucleophile for my reaction. But generally I'm always there. So like if people, wanna like, cause I always prefer teaching in person anyways. Don't get me wrong. I like teaching, I don't mind teaching through Zoom, because like the way I do it, I use OneNote, so it works out the same way. But it's like certain things, like when you describe like with the model set or whatever, just works out better, right? So
is he gonna let us use a model kit on the exams?
That you don't really need to use a model kit for Argo 2, because you're not going to be really asked for like enantiomer stuff. I mean, you will have to understand like, when things form enantiomers or stuff, but you're not going to be asked those basic questions that you were in Orgo 1. It's more focused on the chemistry, and this is I would say this class is very reaction and mechanistic heavy, definitely, especially like if you guys want to go and peek around, chapter 18 or chapter 19. Oh, if you look at the end of chapter 19, that shit will scare you. There's a lot. I mean, when I first saw it first time, I was like, whoa. But then you realize, like I said, so much of those things are the same thing. They're just slightly different. Anyone else have any other questions? Like I said, still around. I could still stick around for like 10 minutes.
So I'm actually really happy that you said you're going to be on campus mostly all the time, because I need a lot of help. What times are you there on Mondays or like Wednesdays and Fridays?
Mondays I'm usually there till like 7 or 8, but I mean it depends. So Monday Friday I'll be less free now, especially because we're gonna have group meetings with our lab group. So Fridays, I mean, that might be available later in the day, but Mondays, like I said, it all depends on what reaction I'm doing that day. If I'm setting up screens in the morning that I'm going to be checking later at night, then I have like a 3-4 hour period where I'm kind of just sitting around or, just, cleaning up some extra lab where I'd sit around from a week ago or whatever. So I'll usually just let people know in chat. Like if, I don't know if I can let you guys into the CDI, but I have a room in Marshak, 1102. It's on the 11th floor. It's like, it's actually a little place. I mean, it's not open throughout the week, but I mean, I could open it for people. Actually, I have to ask Professor Kovac if I could open it. But it's like a little, it's a chemistry, like the club room at Baskerville Chemical Society. But it's like a little lounge area, you could just go there, meet up. I used to always like teach on extra time there. So like, that's probably where I would meet people because I don't think I'm allowed to let people into the CDI. I'm not trying to lose access to the building. So, but I could definitely meet people in Marshak or whatever. I'll just let you guys know throughout, like, I'm on campus right now. I'm not doing anything. I could, help some people out if they're around. But usually it's gonna be through Monday through Wednesday. Thursdays, most likely not. And Fridays, if my group meeting ends fast enough, then probably later in the day, depending on whatever we do. But yeah, I mean, it's kind of something I'll just let you know throughout the semester whenever I'm available. Or if you ask, right, that's the thing. You could just ask in the group chat and I'll let you know if I'm available and I'll come over to Marshak or whatever.
Are you going to be available on Monday?
This coming Monday? Honestly, I'll let you know by the morning because it all depends on what I'm setting up. Yeah. Like I said, it's a day-to-day thing. That's what I was trying to get at in the email. And like you could just ask me again on Monday and I'll let you know probably. Because right now what I'm doing, it's actually funny that we did ethers today. So the molecule that I made, right? So this is OH, this is a phenyl group. CO, right? So I actually basically did a Williamson ether synthesis. It's just intramolecular. And the base I use is terbutoxide because it's a lot easier to work with and it still accomplishes the same thing. Terbutoxide, not a good nucleophile, strong base. This deprotonates this, right? Form this. And now in this case, which is why this was kind of an example I wanted to do earlier, right? Now you have an intramolecular reaction because this is the alkyl halide, right? And intramolecular reactions occur a lot faster than intermolecular, right? So this gets in, kicks off, right? And I just made and purified this yesterday. And this is something called an oxetane, right? And then what eventually I'm going to do, so right now, this was kind of a nucleophile and electrophile all in one. And then eventually what I'm going to do is I'm going to stanylate it, which means I'm going to basically attach a tin group here, right? And then you do something called Stille coupling. But I can't really talk too much about that because I don't ever get how much you could talk about your research. I tend to just briefly describe it because I love relating it to what we're doing. But like at the same time, the stuff isn't published yet. So like, gotta make sure you don't, say everything. But it's funny that we did ethers because this is a cyclic ether, just known as oxetanes, right? A four-membered, it's like an epoxide actually, it's just four-membered, right? And that's the current chemistry I'm working on is Stille cross coupling using oxetanes. Hopefully eventually open chain molecules of this. Basically this last month, I've just been optimizing a reaction, literally running this reaction with the same electrophile, probably at 20, 30 times. And I've gotten it from like around like 20-ish% to like 40-ish%. The best yield I ever got still was like 51%. So that's what I was saying earlier. It's just like, there's only so much you can do sometimes for certain reaction. Who knows? Maybe, I don't even know if I could get it past that 51 mark. Maybe I can. But that just comes down to whatever is happening in the reaction vessel. And that's why I like computational chem because I feel like it's the bridge in understanding it a little better. Yeah. Anything else? Anybody? Orgo 1 stuff, Orgo 2 stuff. Oh, also, I guess I should mention this now. Since someone asked me for those, there's only 9 people here, but for those who are like pre-meds or chem or biochem majors, so, there's like a club called the Baskerville Chemical Society. I think they're trying to do meetings, Zoom or something, but they have a lot of like access to like information, whether it's pre-med or chem related, and, just helping people out in general. So if you're interested in that, I think Kayla Hernandez is the treasurer, I want to say. I forgot the e-board. It's like people I don't even know. But yeah, you could talk to her about it. I don't have her email. I'll probably plug it in next time. Anyways, yeah, if that's
Yeah, thanks
it.
so much.
Yeah,
Appreciate it.
have a
And
good night.
have a good night.
You too.